All right, calculus. Today we're going to talk about properties of limits and trig limits. So here are the properties of limits. That just says if you're taking the limit as x approaches 0 of one function f and another function g, if both limits exist, then the sum of, or the limit of the sum, so the limit of adding the two together, is the sum of the limit. So you can just split it up and take the limits separately and add them together. That is the same with subtraction, it is the same with multiplication, and it is the same with division. Okay, so real simply, the limit of a sum is the sum of the limits. Same with subtraction, multiplication, and division. And then you can always take a constant here and just move it out front. Okay? All right, so let's do some trig limits. So first, evaluate the limit. What's the first way we evaluate a limit? Always, always, always direct substitution. So we are going to plug in 2 for x. So that is the sine of 2 pi over 2, which cancels, which is the sine of pi, which you should know from your unit circle. If you need to draw a quick one, pi is over here. That's the point -1, 0. Y is sine, so the answer is 0. All right, number 2, we're going to plug in 7 for x. So we have the cosecant of 7 pi over 6. 7 pi over 6, so you need to do a quick sketch of that. So this is pi right here. That's 6 pi over 6, so we need to go a little bit more. So right there is 7 pi over 6. What point is that? Well, that depends how you do it. I call them long, short. So this is long to the left. So the long one is -√3 over 2. Short is 1/2, and we're going down 1/2. So that is the point there. Cosecant is sine flipped. This is sine. Flip it. We get -2. And then the limit as x approaches 3 of 7 is just 7. All right, so now let's do some fun trig limits. So in order to do those, we've got these two special cases. And there's this whole big long thing if you can see why, but really we're just gonna say as x approaches 0 of sine x over x. So I gave you that picture here. If I'm heading to 0 from both directions, then I'm heading to the y value of 1. And if the limit as x approaches 0 of this function here is 0. So these are two things you just need to know when you're doing limits, okay? There's a couple variations. Sine x over x is 1. If you have the same constant out front, it's just c over c, which is still 1. If these constants are different, then it's a over c. Here, if these constants are same, it's still just 0. So a couple variations on that same thing. All right, so in order to do trig limits, if we get that indeterminate form, we need to rewrite it somehow. And typically that's using trig identities. And then maybe we use one of our 2 new memorized limits. So what's the first thing that we always do? We do direct substitution. So we're going to plug in 0. That is tangent of 0 over 0. So where's 0? It's right here. That's the point 1, 0. Tangent is sine over cosine. That is y over x. That's 0 over 1, which is 0. So tangent of 0 is 0 over 0. This is indeterminate form. This means we must be able to rewrite it in some way in order to actually do the calculation. So we're going to rewrite tangent as sine over cosine. So we have the limit as x approaches 0 of sine x over cosine x over x. Now that's an messy complex fraction, so how do we do that? Well, if we're going to simplify sine x over cosine x, And we can't divide fractions. We must multiply by the reciprocal. So we get the limit as x approaches 0 of sine x over x cosine x. And then we just did this right here. Sine x over x, the limit of that. So we could rewrite it as the limit as x approaches 0 of sine x over x times 1 over cosine x. And then our properties of exponents say that the limit of a product is the product of the limits. So if we wanted to, we could rewrite it. If you're not thinking through it as well, you can rewrite it as the limit as x approaches 0 of sine x over x times the limit as x approaches 0 of 1 over cosine x. And our special case here is limit of sine x over x as x approaches 0 is 1. So this is 1. And the limit as x approaches 0 of 1 over cosine x, well, let's do direct substitution there. That's 1 over cosine of 0. So that's where 0 is. That is the point 1, 0. So the cosine of 0 is 1. So this is 1 times 1, which is 1. All right, so there on that problem in particular, we use the tangent of x equals sine x over cosine x. We also have all the reciprocal identities and the Pythagorean identities that we might have to use. Sine squared plus cosine squared equals 1 is the one we use most often. All right, so first thing we're going to do is direct substitution. So that's cosine of 0, tangent of 0 over 0. So in the last problem, we found that the tangent of 0 was 0. So we get 0 over 0. So this is indeterminate form, and we got to be able to do some rewriting in some way here. So I'm going to write tangent as sine theta over cosine theta. So we have the limit as theta approaches 0 of cosine theta times sine theta over cosine theta. Hopefully you're seeing there what's going to happen over theta. Cosine over cosine cancels. And so we get the limit as theta approaches 0 of sine of theta over theta. That is our special case of 1. That is our special case that we memorized of 1. All right, next example. We're first going to plug in pi over 4. So this is 1 minus tangent of pi over 4 over sine of pi over 4 minus cosine of pi over 4. So we need to know our coordinates at pi over 4. It is the point root 2 over 2, root 2 over 2. So tangent is y over x. That's root 2 over 2 over root 2 over 2. Anything over itself is 1. So this is 1 minus 1. Tangent of pi over 4 is 1. Sine is root 2 over 2. Cosine is root 2 over 2. 0 over 0, indeterminate form. That means we have to do some algebraic manipulation here. We got to do more work. So I'm going to write tangent as sine x over cosine x again and see what I can do. So we have the limit as x approaches pi over 4 of 1 minus sine x over cosine x all over sine x minus cosine x. So this is a complex fraction, and we've got two methods to simplify that. I am going to use the one where we multiply. So I'm going to multiply. I need to get rid of this little pesky denominator. So I'm going to multiply this whole top by cosine x. I'm going to multiply this whole bottom by cosine x. I'm going to distribute that in here. And so we have the limit as x approaches pi over 4. Then on the top, I have cosine x minus, I have sine x over cosine x times cosine x. The cosines cancel to give me sine x, which was the purpose of doing that, so that they'd cancel, over cosine x times sine x minus cosine x. So those two subtraction terms are opposites. That means if I take a negative out of one of them, then they will be the same. So I'm going to rewrite limit as x approaches pi over 4. I'm going to take a negative out. If I take out a negative, that's going to give me negative cosine x plus sine x, which I'm going to rewrite as sine x minus cosine x over cosine x times sine x minus cosine x. And these cancel. And so we have the limit as x approaches pi over 4 of negative 1 over cosine x. We plug in direct substitution. That is negative 1 over cosine of pi over 4. Cosine of pi over 4 is root 2 over 2. Negative 1 over root 2 over 2. How do we divide fractions? We multiply by the reciprocal. So negative 1 times 2 over root 2, which is negative 2 over root 2. Rationalize the denominator, root 2 over root 2. And we have negative 2 root 2 over 2, which is just negative root 2. Whew. All right. This is our special case. How do we know it's our special case? What do we look for? We look for x is approaching 0 and sine of something x over something x. So if this is a 1, this is that a over c special case. This is 4 over 1 or just 4. Example 5, we are going to plug in here. And we get 1 minus cosine of 0 over sine squared of 0. We draw a quick unit circle. 0 is at the point 1, 0. So cosine of 0 is 1. So we get 1 minus 1 over 0 squared. 0 over 0. Indeterminate form means do more work. So what are we going to do here? So we don't have, usually we just try to write everything in terms of sine and cosine. So here we're going to have to use our Pythagorean identities, which say sine squared x plus cosine squared x equals 1. That means sine squared x equals 1 minus cosine squared x. Oh, this one's going to get fun. So we have the limit as theta approaches 0 of 1 minus cosine x, theta, 1 minus cosine theta on top, over 1 minus cosine squared theta on the bottom. So if you're struggling at all using trig, you could think about it if it were just regular terms. This is like 1 minus x over 1 minus x squared. Hopefully you would see you factor the bottom. That is a difference of 2 squares. So I'm going to factor the bottom here. So on the top, we're going to leave 1 minus cosine theta. On the bottom, I get 1 minus cosine theta, 1 plus cosine theta. The 1 minus cosine thetas cancel. And we have the limit as theta approaches 0 of 1 over 1 plus cosine theta, direct substitution. I plug in, that's 1 plus cosine of 0. Cosine of 0 is 1. 1 over 1 plus 1 is 1 over 2. All right. Oh, look at that. That's it. So trig identities get a little tricky here. I try to give you really simple ones, so don't get too caught up in it. Pythagorean identities and then just changing things into sine and cosine usually will be sufficient. Maybe a tiny bit of factoring like we did on this problem, but not too crazy, not so crazy like you got in pre-calc. So take it easy and have a little patience and work through these and let me know.